Our next talk is from our sponsor Synopsys, Dan Benua. Dan has been working on formal verification methodology and deployment at Synopsys for 15 years. He currently leads a team developing advanced formal verification engines that helps direct the development of a unified verification platform described in this talk. Dan received the MSEE degree from Stanford University. Outside the work, Dan enjoys building and flying experimental aircraft. Leveraging formal and an integrated, the title of the talk is Leveraging Formal and an Integrated Verification Platform.
Thank you. Actually, my slides don't quite agree with that. I'm going to talk a little bit about verification compiler and formal, how that leads into our solutions for formal verification at Synopsys. So what is verification compiler? This is an announcement that Synopsys made a couple of months ago in the press that was probably little noticed by anyone except our competitors, of course, noticed it, I'm sure. At Synopsys, we were, of course, founded on Design Compiler, and years later we had something called IC Compiler for physical design, and now we've finally unified the Synopsys EVA tool portfolio on the verification side with Verification Compiler. And in this talk, I'll introduce what that is, why we did it, and sort of focus down on how it impacts our strategy in formal and static verification. So of course, we have to start with some obligatory marketing slides to motivate the talk. This curve on the screen here is, of course, representing the bug finding history of a typical project, where the bug finding rate starts quite low while you're setting up the verification environment, then it increases and finally tapers off, and you can't really call the project complete or taped out until it does taper off. So what everyone is focused on in the industry now is this concept of shift left to try to accelerate finding bugs, to improve time to market or time to emulation or time to software development for the system level. So the approaches to address that we're advocating are increased focus on static and formal verification, automation, of course, verification IP, and everybody loves faster simulation and debug, so that of course, has to be part of the solution. Okay. So in this talk, we'll focus specifically on the static and formal part. And then, of course, every marketing pitch has to have the up and to the right curve. In this case, the up and to the right curve is referring to the cost of bug fixing. As time goes on, it becomes more and more expensive. And this, of course, justifies why the increased focus on front-end verification activities like static and formal verification. So what do we mean by static and formal? Well, we'll start out with simulation, of course, because simulation is the workhorse of functional verification. Simulation has a lot of nice attributes. It scales very well to extremely deep sequences of states. It handles extremely large designs. It does run out of performance, though, in some respects. As the design becomes more and more complicated, there are more and more paths that the state space could be traversed, and it becomes harder to close coverage. So the time to, as complexity increases, simulation becomes less and less effective at coverage. Static verification refers to techniques that are vectorless. They don't deal with state space behavior, but more with structure of the design. And certain classes of bugs can be identified or ruled out just by studying the structure of the design. The simplest types of static tools are lint tools that look for poor coding style, but they're much more sophisticated structural analysis tools related to clock domain checking or power architecture that can detect bugs purely on the structural basis. Of course, formal, as you all know, is much more like simulation in the sense that it's examining the behavioral state space of the design, but in an exhaustive way within the limits of capacity and depth. So formal verification is a nice complement to simulation, but with different characteristics in terms of coverage versus scalability. So what we are postulating is needed is a comprehensive solution that encapsulates all these technologies in a single platform. So this is where the verification compiler concept is coming from. And it incorporates both static and formal checking, verification planning, coverage closure, and of course the workhorse simulation and debug tools. So the motivation or the potential benefits for doing this are performance and productivity. We're particularly focusing on the SoC level rather than the IP block level, because we think a lot of the problems that companies are having today are related to this SoC level scaling. Of course, we can simplify adoption, ease of use by merging these things together into a single platform and provide kind of a single focus for achieving functional verification tasks. This is a picture from Google of a bunch of SoC block diagrams, and a lot of the modern SoCs we see have very common problems in the verification space. Power management is becoming ubiquitous. Of course, everyone knows about the portable battery-driven devices requiring advanced power management, but even large servers now, power is becoming a dominant dominant factor in the cost of ownership of servers. So even people that plug into the wall are starting to be much more concerned about power. More clocks and greater complexity in SoC drives more clocks, more protocols and buses, and complex interconnect. So from this point, I'll address the static and formal part of the verification compiler, because I think most people are familiar with Synopsys simulation technology. We have debug technology that was acquired from SpringSoft. We also, of course, have emulation technology that's also recently acquired, and we've made a big investment in verification IP. But in the low power, in the formal and static space, the areas that we're focusing on are low power static checking, CDC checking, formal verification of several different types, which I'll go into, and lint checking. And there's nothing revolutionary about these. These are, in some ways, technologies that Synopsys has offered for many years as standalone point tools. What's new is the way that we're combining these things into a single platform, which involves really re-architecting them from the ground up. We started with the concept that we needed to apply these technologies at the chip level, not at the IP block level. So we needed the capacity to read in full chips. And full chips today are enormous and becoming more enormous. So this required a completely new rethink about how we store the design in the machine for analysis with these different techniques. So we built a new database that actually is proving to be quite successful at reading in chip-level designs. And the key innovation in this database is that it maintains word-level structure. So the design is not bit-blasted. We preserve word-level structures and memories. So a huge two-dimensional memory can be represented as a single node in this database. And that, of course, saves a tremendous amount of memory. We have a set of readers that are common for all the tools that work off this database. We use the VCS front end for reading HDLs. We have UPF readers, Tickle script interpreters. We basically support all the design formats that are common in the Synopsys ecosystem. On top of this database, we've built new analysis engines, some of which can take advantage of the word-level structure of the database. Not all, since for some types of analysis you do need to bit blast to do the checks. But whenever possible, we take advantage of this compact representation. The result, comparing the new tools to our previous generation technologies is, as we had hoped, orders of magnitude or high factor speed-ups and capacity improvements. In many cases, we can process designs that we were unable to process with previous generation tools, and where the tools can produce equivalent results, we're seeing anywhere from 2 to 100x performance improvements driven by this new architecture. Let's see what becomes. I should say something about the availability of this platform. We don't have everything that I'm going to talk about today. We have a lot of it. The low-power static checking technology has already been in deployment at multiple customers for a year and a half, but the CDC and formal technology solutions are just coming out now. Some early partners are using them, but they haven't become generally available yet, and the language checks are not due out until later this year. So in formal verification, the things we've focused on are a unified user interface. It's much more like Design Compiler. It's all based on Tickle. So any designer that's familiar with Design Compiler's command language, DC shell language, will find that the formal tools use the same commands for reading in designs, has the same design query capability, scripting capability, but there's just a few commands that are added new that are specific to formal process. We have new formal engines that have been developed by an in-house team we've been working on for several years now. Of course, we had engines from our previous generation, but we've added a lot of new technologies that have proven important for some of the new applications that we focus on that I'll talk about in a minute. Orchestration is an important part of formal verification technology. This is the selection of engines, what's the right engine to run on a certain type of property, and also how to parallelize problems. Many of these formal verification problems are very amenable to parallelization on a server farm. And we found that for the hard or large SOC level type problems, the way that you manage or partition and distribute the problem across a server farm is critical to achieve good throughput. Of course, we want to support all the features. The formal verification is a very competitive area. I'm sure many of you know. There's all new apps are coming out all the time, and new ways of applying formal verification. And of course, we want to support all of those methodologies as well. The other key area is debug. Verdi has taken its place as the key debug interface for all of the Synopsys verification tools. Of course, Verdi has dominated in simulation debug for many years. And our challenge in this new platform is to expand Verdi's capabilities to better focus on static verification. Sort of the basic features are the things that you would expect from a property checker. Of course, we have all the common features like automated property generation for simple auto checks, formal scoreboards, coverage analysis is all integrated in with the simulation coverage databases and reporting tools. We have a connectivity checking solution. Some previous speakers spoke about connectivity verification. We also address the coverage problem, which is also talked about in a previous paper today. And our approach is based both on line and condition coverage and traditional simulation coverage metrics, but also on using Certitude, which is a mutation injection engine that Springsoft pioneered for simulation. We can use that engine for formal verification coverage reporting as well. And that gives a very fine-grained analysis of where bugs could actually could be inserted to cause assertion failures. We have a new capability in sequential equivalence checking, which I'll talk about more in a later slide. And then finally, for the CDC and low power are primarily static structural analysis applications, but there is some behavioral component to them that we can address with formal verification or simulation. For example, in clock domain checking, you're often interested in stability criteria for fast, slow transitions or gray encoding. Those are behavioral properties. In low power, we're interested in power up and power down sequencing and in UPF power state transition verification. As far as the interface, I mentioned before, it's very much like DC shell. In fact, many of the DC shell commands are supported. Of course, additional commands are required in order to set up the reset state for formal verification, to select properties, to, of course, run the checks, filter the results, and create reports. There is a graphical user interface in addition to Tickle. For general counterexample debug, it looks just like Verdi simulation waveform debug. That's a common paradigm that I think pretty much all formal tools use and all designers are comfortable with. But in addition to that, we've added customized windows for reporting on what's happening in the engines, which engines are being successful on which properties, and also for more specific analysis that's unique to formal verification, such as identification of complex structures in the cone of influence of a particular property. We can find out where are the FIFOs and where are the arithmetic operators and the other constructs that could be causing difficulty with formal property convergence. I mentioned a moment ago about sequential equivalence checking. This actually also came up in the previous paper just before lunch about fault analysis or fault propagation. Sequential equivalence checking is a technology that compares two RTL designs to see if they're exactly the same at their outputs, but not necessarily the same at internal structure. So it extends on the common Boolean equivalence checkers that require state point matching to scenarios where the design is changed in ways that are not compatible with Boolean equivalence. And the most common example, of course, is latch-based clock gating. The majority of users of this technology are doing clock gating insertion, and they want to make sure they haven't corrupted the function of design. But there are actually a number of other microarchitecture changes, such as resource sharing or resource duplication, that don't change the sequential behavior of the design at the boundary, but substantially change the microarchitecture. And we can verify equivalence in those cases as well. This chart is sort of categorizing the different types of equivalence checking technology that we support in our business unit. I haven't talked up till now about Hector, but Hector is a product that we started offering about 2 years ago, I guess, that does transaction-based equivalence between C and RTL, or between two C models or between two RTL models. Basically, if we can compile it and it's transaction-oriented, and we can map the inputs and outputs of the designs between the two models, we can do this transaction equivalence. I thought it was actually the previous talk describing how you abstract these hardware models made me think a lot about how it's very similar to how we develop a model, an abstract model of C behavior in order to do equivalence checking against an RTL implementation that possibly has different timing. And then I was just talking about the seq, which is the cycle-accurate equivalence, and then we have formality, which is really targeted towards synthesis verification, RTL to gate, Boolean equivalence, and it does require state matching or some communication from design compiler about retiming optimizations that have been done during synthesis. Oops, I pushed the wrong button here. Let me see if I can get it back. There we go. Connectivity checking, this is one of the applications that I think all the vendors are offering now in the formal space. What's unique about our solution here is our focus on debug. We don't look at connectivity checking as a traditional formal problem because in formal verification, when you get a counterexample, you want to look at the waveform. In connectivity checking, when there's a failure in connectivity, a waveform is virtually useless because all it tells you is that the value at the input and the output are not the same. You have no idea why. So the combination of structural analysis and also behavioral analysis of mux controls is really what's needed to find the bugs in connectivity checking problems. And we've invested in both structural analysis tools that try to isolate those root causes of connectivity failures, and in a graphical, schematic-based debug environment that helps you understand what the logic is between the connectivity points. So that's kind of the marketing section of the talk. And just before I wrap up, I wanted to talk a little bit about some of the technical problems in scaling these applications to chip level. The whole concept of apps in formal is to try to reach users who are not formal experts, who don't understand really what's happening in formal. They're just trying to verify some attribute of their chip. Typically, they're familiar with simulation methodology, but not with property checking or writing assertions. So all of these apps in coverage, CVC, power, connectivity, security, or control register verification are amenable to formal, but often the user of them doesn't really understand what's important or what's necessary to set up a formal problem or the impact of improper setup. So the challenge is how do we deal with the reality of chip level problems? First of all, how do we infer clocks and reset states for these formal assertions that we want to check? For us formal guys, it's obvious we figure out what the clock is and we abstract the reset state, but the simulation guy doesn't know necessarily what the clocks are or that are driving different parts of the design, particularly in a multiple clock design, or how what's the correct reset state for this verification. Black boxes are often an issue at the chip level. There may be things like analog circuits or test bench artifacts or other things that don't matter for a particular property verification. But how do you figure that out? And do you have to have the user do that, or can we do it automatically? Test bench code is nice when it's isolated from the design, but we find that it's not always isolated from the design. People are often inserting test bench code in the middle of their RTL code in pragmas or in models of parts of the circuit that are not going to go through synthesis. So we have to deal with that as we make a formal model. So a lot of the problems of building up the formal problem are very different at the SOC level than they are at the more controlled IP block verification level. So some of the solutions that we see are important are, first of all, automation. We want to leverage the static analysis capabilities of our platform and behavioral information that we might have from simulations to figure out what the clocks are, what the resets are, extract invariance from simulation, for example. This is data that we can just gather kind of automatically, but then it needs to be validated. So that requires user input. So what kind of user interface do we need to provide so that the user who doesn't understand formal can help you refine this setup? And then finally, methodology. The order that verification tasks executed can have a big impact on how the tools can reuse information from previous steps to make later steps easier. So these are all areas that we think the platform approach will give us a lot of benefit and allow us to significantly increase both the power and ease of use of these formal apps at the chip level. And with that, I will wrap up and take any questions.
Thanks, Dan. Any questions for Dan? On the way down, I have one question, Dan. Can you just explain what you're doing with combining certitude with formal? Is there any...
Combining circuitry?
Certitude, sorry.
Oh, certitude, yeah. Certitude is used in simulation to rate the quality of a test bench by injecting mutations into the design, seeing if the test bench can both sensitize the mutation, propagate it to an output, and then see if any checker in the test bench actually will detect the mutation. And we can do the same thing in formal verification to qualify a set of formal constraints and checkers to see both if those things can be sensitized and if they cause any assertion to fail. So it's used as a coverage metric or completeness metric for a formal setup.
So I guess the interesting question is, can you combine the simulation and the formal to see if the combined effort?
Potentially, if the assertions are reused in simulation, they can be combined, but typically the constraints in simulation and formal are completely disjoint.
No, not the constraints, the fact that you're combined, if you add your simulation, what you've done in simulation, what you've done in formal, combine those, the two sets of results that demonstrate that the combination is sufficient to find all those bugs, all those mutations. You're not looking for bugs in the test bench, you're trying to find if your simulation certitude is trying to find out if your test bench is good enough to find the bugs.
Right.
So the combination of simulation and formal, is that good enough to find the bugs?
Yeah,
that would be the interesting question of certitude.
Yeah, you could argue that if a mutation is found in simulation, that you don't need to find it in formal. But I'm an advocate of having a lot of overlap between what's verified in formal and what's verified in simulation.
Okay. Okay. Okay, thank you. Yeah, I agree that overlap can be good, but the budget holder may disagree sometimes.
Hi, so you said you'd re-architect your database so it supports word level and other aspects of the design storage smaller. Have you created formal engines that support word-based?
We have looked into word-based formal engines, but we haven't yet found a significant advantage from doing that. So most of our formal engines, in fact, really all of our formal engines, do use a bit-blasted representation today. I think this has to do with, that in the end you get to a SAT solver at some point, and that seems to be the most effective technology, and that requires bit blasting.
Another question is, have you used the formal engines in your certitude implementation to take advantage of details that the engines can provide to produce a more efficient run on certitude? Or?
No, actually, not yet. I mean, we don't have our formal engines really in certitude. It's more that certitude collaborates with the formal engines to prove properties on mutated designs. So we're not using the formal engine. And certitude does have technology to optimize faults, because the number of faults that it can inject and times the number of assertions blows up into a huge number. So you can't check every combination. So it does have optimization techniques to minimize the number of runs that you need to do.
You said you just use SAT rather than SMT, I guess, as your solving engine. And that surprises me a bit, because I thought earlier on in your talk you described a single node for a large memory array.
and that would be a natural map onto array theory in an SMT solver. Whereas if you blow it up into bits in SAT, it must be very expensive.
Yeah, if we have to blow up a memory to solve a SAT problem, that is not going to be very effective. Our engine guys have looked into SMT solvers, and so far they've decided that they're not giving us an advantage for the kind of problems that we're seeing. So that could change as we see new kinds of problems and as SMT solvers improve. But today we have not incorporated any SMT solver.
Is Hector word-based or is Hector bit-based?
Hector is could you repeat the question? Is Hector word-based?
I thought when I listened to talks by Theo Drain that it was very much word-based. Hector.
Well, Hector uses this word-based architecture, but the solvers themselves are not word-based.
Okay.
Right. Thank
some
you.
tough questions.
Yeah.
Thank you.